Okay, so like I said, this is the last portion of the transport chapters. Where we've done diffusion. This is viscosity. There are some other things in the transport chapters that we're not going to be talking about. We talked about thermal conductivity, but we're not going to get into ionic conductivity or sedimentation. But those are also just as important. But it's the same kind of skills. You have a gradient and you have a flux that's in opposition to that gradient. And in those two situations, ionic conductivity would be the flux against a conductivity in charge or a gradient in charge. And then sedimentation is kind of interesting. That's how all of our centrifuges, that's the technology that our centrifuges are based upon. So you set up a gradient in terms of gravity. And so then you have flow in opposition of that gradient. So you can use that for sedimentation, and there's some certain things you can do with the sedimentation boundaries. So in terms of transport, we're in the viscosity area. So this is a gradient in linear momentum. And it's linear momentum because we're talking about laminar flow. And we'll discuss that in a second. And so now instead of particles being our gradient, it's going to be flow, so velocity across a surface. Now it's easiest, I think, to envision this in a pipe, okay? But it's really just flow above a surface. So we're talking about laminar flow or layered flow. That word laminar is kind of a strange spelling, but if you think about a countertop, you have a lamination or laminate top that's layers. And so think of this flow as layers. Kind of like a countertop with multiple layers, only it's a velocity gradient, so the layer that's touching the wall of the container is not moving. Otherwise, the container would be moving. So the container's still and the fluid is flowing. And so it has to go from stationary in contact with the container wall to flowing above that surface in some distance. Okay. So that's the gradient that we're talking about. It's a strange gradient. It's not a gradient in matter. It's not a gradient in temperature. Okay. It is a velocity gradient. Okay. Which, if you take into account the mass of the particles that are moving, then it's a momentum gradient. And so here we have this velocity gradient. Up here at the top, the particles are moving quickly, say from left to right. And down here, they're stationary when they're in contact with the surface. And so you have this gradient. And so this is, again, going uphill. The gradient goes up. And so then the flux would be 90 degrees to that. It would be downhill towards this. So what it's saying is that this high velocity gradient is putting force on the slower molecules, okay, and dragging them along, okay. And so here's the derivative of velocity with respect to the z coordinate, and that coefficient is the transport coefficient, which is the viscosity. That's the eta. The Greek character eta is typically used for viscosity, and for an ideal gas, it has the average velocity, the number density, the mean free path, and the mass of the particle. And so this viscosity is a resistance to flow. You can think of it as sort of the simple terms, the layman's definition. And so we can calculate this using the ideal gas condition for argon at room temperature in 1 atmosphere. There's several substitutions going on here. They've got substitution for the number density. And then for unit's sake, we go from the molar mass in grams per mole to kilograms per mole. So that's why I've capitalized it here. And so then just using this term, we can also break out that mean free path, and we end up with the molecular cross-section here. And some of the temperature terms and gas constant, et cetera, cancel out. And so this would be a simple form to use. We've got the average velocity that we calculated earlier in class, the molar mass of argon, Avogadro's number, and then we calculated that collisional cross-section for argon in an earlier lecture. And so these are all the terms for argon. And so we end up with these SI units, 58 times 10 to the minus 7 kilograms per meter per second. And this has a strange unit called poise. And poise is 0.1 kilograms per meter per second. And so one of these, this 10 to the minus 7, can be broken into a 10 to the minus 1 times 10 to the minus 6. Right? Everybody cool with that? So you've got a 10 to the minus 1 and a 10 to the minus 6. The 10 to the minus 1 kilogram per meter per second is a poise. See, 10 to the minus 1 here. And so then the 10 to the minus 6 becomes micro. And so this would be 58 micropoise, or 58 micropie. So that would be for argon behaving like an ideal gas, very, very low viscosity. So you could flow argon very quickly. And the velocity gradient would be very, very small and very, very close to the walls of the container. Now, water is centipoise. So argon in terms of micropoise, water is centipoise. And there's also, if you look up viscosity, if the place you look it up is typically on the internet, it's pretty sloppy in terms of the units for viscosity. And you'll see Stokes and you'll see poise, and it won't describe which one it's talking about, but Stokes is actually called kinematic viscosity, which is a slightly different term. Okay, kinematic viscosity is the viscosity in poise divided by the density. And this can be confusing, and I'm saying this because I got trapped by it at one time, is looking up viscosity. And what if you're going to sort of look at the units, a lot of times you just look up the properties of water, right? So just such a common substance. There's a ton of data out there on water. And so you look up viscosity for water, and you get 1.0020 centipoise, and then you see it listed as centistokes, and you might make the incorrect assumption that Stokes and poise are the same thing. Right? And it's not true. But because water has a density of 1 gram per mil, you got fooled. Yeah, it just works out that way. They're not the same units. Okay, but you could be fooled if you just happen to use water as your number or as your substance to look that up. And I was fooled by that one time. Yes.
So is the surface like frictionless? This wouldn't matter because you said that like molecules, whatever, lining the surface don't move.
Right.
So if they would move, wouldn't that create friction, and then heat would change the problem?
The molecules that are trying to move are imparting a force onto the surface, and so you can actually get the surface to feel a force by flowing something through a pipe or across a surface. In fact, that's how they actually measure viscosity, is the drag it puts on the surface. So if you look at a rheometer, which this is rheology, the science of flowing fluids, they'll have plates and cones and cups. So you have a motor that drives this cone. Let me just draw it. So you have a motor that drives this cone. And so the motor is turning this cone back and forth, right? And so it's imparting a velocity left and right, left and right. And inside this cone, you put your fluid, and there's a little receiving vessel. And so your fluid is in here. And you're basically moving one plate and seeing what happens to the other plate. Only it's just a geometry like a cone, so it'll hold the fluid. And then down here, you've got a detector that's measuring the imparted velocity. So you can see if the motor drives this very quickly and the detector is detecting the same motion as the motor, there's a really strong connection between these two, and that would be a very low velocity gradient. Because as soon as this one turns, it drags this bottom one down, and there's really no gradient between the velocities. And so that would be a low velocity gradient, which was a high viscosity, because the viscosity opposes the velocity gradient. And so if this motor can spin freely and this one never turns, then you don't have very much viscosity at all, because they're slipping. And so this is one way of measuring these properties. The way we measure them in the lab is with the falling ball viscometer. And so you just have a ball and gravity's pulling down on that ball, and you have some timing marks. And we have a video set up so that we video the ball and it goes through the top timing marks, and then we have some optics set up to where we can video and see in the same video the bottom timing marks. And the nice thing about using video is you can go get the frame at which it passed this mark, and the frame at which it passed that mark is 30 frames per second. And so you can get a very accurate measurement. You could do this one by hand with a stopwatch, but you don't know if you really made a mistake or not, because you're watching and you try to be good with it going through those, and it's operator dependent. I mean, we all have different reflexes. Whereas if you video the falling ball, then you're able to go back and check your work. Now this is going down, so the water has to squeeze, or the fluid has to squeeze through this defined little gap here on either side. And so that's a velocity gradient between this ball falling and the stable or still outside of the wall. And so that's proportional to viscosity. So it's another way to measure it. Now, surface roughness would just interfere with that laminar flow. So the laminar flow, I don't know if you would have to assume it was frictionless, though. You know, that's really the question that I'm stumbling on. I don't know if you have to assume it's frictionless, but I think it's probably a safe assumption that it's a smooth surface, because we're just taking layers of velocities. So does that answer your question?
I think somewhat. I don't know, because there's some like weird stuff my aerospace friend showed me a while ago about like flow, and it was like after a certain point, it just like randomly like goes all the way down and like approaches zero or something. It just randomly slows down.
Yeah, I don't. But it does. It is weird, because at the surface, if that wall's not moving, then the molecules that are touching that wall are not moving. You know, somewhere between not moving and the full velocity is this laminar flow region. Now, there's also turbulent flow. We're not talking about turbulent flow. We're just talking about laminar flow. And so maybe if they had a really rough surface, you would go straight from the still surface to a turbulent flow situation. I don't know. Yeah. So, yes.
It seems like the ball, wouldn't that be more related to density of the material that it's in? Like,
Yes, and so we're going to do that. This is this week's lab. So you need to know the density of the ball, and you need to know the density of the fluid. Okay, and so you have both of those factors in there, and they're in the equation. You pull those out, and then you get the viscosity differences. So yes, the density of the fluid is part of this, and so is density of the ball. And if you there's a glass ball and a steel ball, and based on the density of the liquids, like if you had a really low density liquid, you could use the glass ball, but use the steel ball, because the glass ball falls so slowly. You know, even a 7-minute video or something like that. Whereas a steel ball takes about 15 seconds, you know, and it's not that bad. Okay, so then let's just, how does this work? How does the viscosity restrict flow? Well, the velocity gradient, if you have a high gradient, then that gives you a high flow. So the viscosity opposes that velocity gradient. And so the viscosity slows things down via interlayer collisions. And so if you've got molecules that are attracted to each other, intermolecular attractions, they're going to slow things down. So water is more viscous than you would imagine it to be in terms of its density and its size. If you think about water being only 18 grams per mole, really small molecule, it should be a gas at room temperature, but it's not. I mean, think about methane. Methane's 14. It's 30, 40, 16. Yeah, and so, water's only 2 more grams per mole than that, and yet it's a liquid that boils at 100 C, and natural gas is natural gas. So those intermolecular attractions are really important in terms of water's properties. And so water has a much higher viscosity than you would imagine due to its size. And so my research in cleaning, this is related to cleaning because if you want to remove particles from the surface, then you want something that has a really low viscosity, because this is a small velocity gradient. Notice how it's if you were to walk up this hill, turn yourself sideways, this is a more gradual hill than this one. And so a low viscosity means there's higher speed molecules closer to the surface, and they can knock that dirt loose. Whereas over here, a high viscosity means a slow solvent speed close to the surface. A low viscosity means a high speed solvent flow close to the surface. And so for our solvent properties, we want to use viscosity as one of our terms, of merit. Like we want a low viscosity solvent. Density also knocks particles around because the solvent carries some mass with it in a small volume. So density is favorable and viscosity is disfavorable. So we want a low viscosity, high density solvent to push molecules or push dirt off the surface. And then we want, for wetting purposes, we want a low surface tension. So we want it to be able to go into tiny little holes. We want it to flow fast through those holes, and we want to have some density, so a good punch. Now there are molecules like that. Fluorinated solvents are fantastic in terms of wettability. They have very little surface tension because the fluorines don't interact with the fluorines. The fluorine atom is not that much bigger than a hydrogen atom in terms of the molecule. It doesn't add a huge electron cloud. It's not like chlorine or bromine. And so there's just not a lot of intermolecular attractions between fluorine atoms. And so that you don't have a high surface tension. And you don't have a high viscosity for the same reason. The fluorine atoms don't really interact with the fluorine atoms on other molecules. And so you don't have a high viscosity, but you do have a high density. In terms of the size of the molecule, you're putting a fair amount of mass in that molecule. And so these fluorinated solvents are great for dislodging particles. That's why the freons were good, the chlorofluorocarbons, and now the fluorinated ethers and fluorinated esters and so on are some pretty good solvents for cleaning. Now, viscosity depends upon temperature. We can know this for the ideal gas. And that's kind of nice that the kinetic gas theory correctly predicts an increase in viscosity with temperature, but it gets really difficult really fast when you get out of the gas phase. So gas phase viscosity we can understand. Intermolecular attractions account for an increase in viscosity above the ideal predictions. And so the ideal gas will give you these lines, and then the actual data is higher than that because the gases do start to exhibit some attractive forces. But as far as liquid viscosity, there's no way to know. It's very difficult. I mean, you can kind of think about it in terms of intermolecular attractions, but some molecules have temperature-dependent shape, and that's what really makes the difference. So because liquids are dominated by intermolecular attractions, you've got to really know the molecules well. Some attractions are stronger at low temperatures and some are stronger at high temperatures. So what's a case where intermolecular attractions might be stronger at high temperatures? Well, not benzene. At benzene, you've got a higher temperature, higher velocity, lower viscosity, because there's not enough time or less time for those benzene molecules to interact with other benzene molecules. But take this polymer that I've drawn on the left. So take that polymer and raise the temperature, and it unwinds a little bit. And now you've got a huge intermolecular attraction because it tangles. And so you raise the temperature of this polymer and the viscosity goes up. You raise the temperature of benzene, the viscosity goes down. And so this is...
Seems backwards.
Yeah, it does seem backwards. Okay. And also viscosity with these long chain polymers can change with respect to agitation. So that's bizarre too. Sometimes you agitate the mixture and the viscosity drops. And you guys have done this a dozen times, right? Dozens of times in your life. I mean, some of you do this every day. You reduce the viscosity of something by shaking it.
Ketchup.
Ketchup is one, but even more so, good ketchup, high quality ketchup, and high quality dressing, like salad dressing. Okay? Those have on the bottle something called Xanthan Gum. You ever seen Xanthan Gum on the bottle? It's a carbohydrate, it has no flavor, okay? Really, it may or may not be too long to metabolize. I mean, it's a cellulosic material, so, you may not be able to metabolize it. So it doesn't really add much nutritional value. So it's only there for physical properties, okay? And so what do you want to do with your salad dressing? You want to shake it so it flows out of the bottle, so the viscosity drops when you shake it because you're aligning the xanthan gum molecules. They flow past each other. They hit the leaf and coil back up and get entangled. And so they don't flow off the top of your salad and down to the bottom of the bowl. Right? Because you want to have a salad dressing you can get out of the bottle, but you don't want it in the bottom of the bowl because you want to see that it's on your salad, right?
Salad dressing.
Yeah, I know. It's the weirdest thing that you would think there's all this physical chemistry even in stuff like salad dressing. And the viscosity properties of salad dressing is a big deal. Because if you get your ranch and it just pours out of the bottle and seems watered down because it doesn't have the xanthan gum in it, you're like, this is cheap or old or something's wrong, And then if it hits your salad and flows to the bottom and you're like, I don't even know how much I put on here, right? So then you put way too much on there. This is all a problem, okay? And it's physical properties and it's viscosity, salad dressing, and ketchup. You don't want ketchup to run to the bottom of your fries. That's not cool. So you wouldn't believe how much CHEM is in food. And so food science is an area that some people go into. I don't know of any schools that teach it, but there are food scientists that have discovered things like xanthan gum and their properties and what it does for their product. So you never know. Maybe something to go into. One time we had an organic chemistry seminar at Oregon State. This guy comes along and he's doing food science and he was looking at muffins and doing NMR on muffins. And so this chemist in the back sitting there looking at you. And so right at the beginning of the talk during the introduction, and he says, so you just take a muffin and stick it in an NMR? And the guy goes, yeah. So, really more like MRI, imaging, the internal parts of a muffin versus the external parts of a muffin and adjusting the recipes to make it just right. I mean, this was crazy, doing NMR on a muffin to get it just right. But I mean, if you're going to do an industrial process that produces 10,000 muffins a month, and they all come out and all the blueberries are on one side because of the way the process works, that may not be what you want. People say, I don't like those muffins because it's all junky inside. I like these muffins because I got a blueberry here and a blueberry there. One in every bite. That's what I like. So we digress a little bit, but my point is to say that CHEM shows up everywhere, even in salad dressing. And so now when you shake it and it flows and it hits your leaves and it doesn't flow, what's going on. So viscosity can be very, very non-intuitive, right? So this is just more with the kinematic viscosity units. And so sometimes you'll see kinematic viscosity, but there's another term too, diffusivity of momentum. And so this is diffusion constant was sort of matter times an area per second. So this area per second is a diffusion term, but then they talked about diffusivity of heat and diffusivity of mass. This has the meter squared per second, so they call this diffusivity of momentum. So you might see that as well. And so when you're talking about, when you see diffusivity of momentum, that's in Stokes, and that's the viscosity over the density. Which again, if you wanted to get to the viscosity, then you would just find the density of that substance and multiply it, and you would get the eta. Now, how do we measure viscosity? This is one way. We've talked about the falling ball viscometer. Modern instrumentation has this motorized version. This is really the best way, using these motorized versions. The reason that the motorized viscometry or rheology instruments are best is because it's frequency dependent, right? If I turn this slowly versus quickly, I get a curve in terms of the viscosity dependence upon frequency. So if you're talking about a motor and you're talking about pistons, you've got a certain frequency that oil has to be able to maintain a certain flow characteristics, and so you would want to know the frequency dependence of your viscosity terms. And you can get that from a rheometric instrumentation. You can't really get that from the falling ball or the Ostwald viscometer. And so this is Ostwald viscometer. You also have timing marks. So you have got this high and low. So you use a pipette bulb to suck the liquid up to the high mark, above it actually, and then you get your stopwatch and start letting it flow out. And when it passes the high mark, you start timing. And when it passes the low mark, you stop timing. And it's going through this capillary. And so that capillary is the restricted area. So that's the measure. That's the thing that's creating the velocity gradient. Now this uses Poiseuille's law, and here's Poiseuille's law, and again it's in several different units, but you've got this change in pressure at the beginning of the pipe and the end of the pipe. Here you've got a slight elevation difference, and so there's a slight pressure gradient, very small. You've got the length of the pipe here, which this has been pulled out and it's down here in the bottom. You've got the radius of the pipe, which is flow in liters per second or whatever, or liters per minute, is dependent upon the diameter or radius of that pipe to the fourth power. And so that's the most dramatic part of this equation. If you think about the flow of water through our water pipes in town, going from a 1/2 inch pipe to a 1 inch pipe is a doubling. And so in terms of gallons per minute, you're not just going to go up and double the gallons per minute. You're going to go up 16 times. 2 to the 4th power. 2, 4, 8, 16. So that's amazing. You can put 16 more gallons per minute of water. If you have 1 gallon per minute going through a 1/2 inch pipe, you can get 16 gallons per minute through a 1 inch pipe. Yeah, it is crazy. And you can put a lot of water through a 1/2 inch pipe. And so to go to a 1 inch is insane. That's really a large jump. If you have the pipe going up, like a standpipe, like a water tower in the city, you have then the density of the fluid, you have the gravitational constant, the height, and the length of the pipe, and the viscosity. So in all these cases, viscosity is in the denominator, and it's to the 1st power. So if you double the viscosity, you cut the flow in half. Make sense? Okay. If you double the pipe, you go up by 16. Okay. If you change the pressure, so we have pressure in here. Pressure is in the numerator, and it's pressure difference. So if you have 1,000 psi at the beginning and 1 atmosphere at the end, so that's 1,000 atmospheres or 1 atmosphere, then you have 999 atmospheres difference in terms of the pressure head. And so that's, again, if you double the pressure, you double the flow. Okay. If you double the length of the pipe, you'd cut the flow in half. Okay. If you double gravity, you double the flow. Okay, so all our water pressure in the city is just by the fact that we have these towers, and that's providing water pressure through all of our pipes. And so it's pretty straightforward.
The length of the pipe is linked from the reservoir to like the source or towards.
Yeah, so you could, if you just had a straight, half-inch pipe from that water tower to your house, and you knew the length of that, and you knew the gravity and how high it was, that's your pressure head, you could calculate the flow.
On the height, would it be from the reservoir to the ground or reservoir to the lowest point of the pipe?
The reservoir to the exit.
Oh, that's what
So it could go underground and come back up, and so it's the difference between the reservoir level and the
like
exit.
That. Yeah, okay.
And that's how siphoning works. So siphoning, you just got to get the exit lower than the level, and so it can go up too.
Mm-hmm.
But if it comes down again and gets below the level, then that's that you've got a head pressure there, and then you'll get flow. And you want to double the flow, double the head distance. Yes.
In the equation, the radius, is that the radius of the capillary? Not the solvent, or?
Yeah, in the asphalt viscometer, yes. And so then, and then the L would be the length of that choke point.
Okay.
So this is also a good point that you bring up, and that is it's going to be restricted by the thinnest pipe that you have. So you might have a 1-inch pipe coming in, you got a half-inch section, and then another 1-inch section. That half-inch section is going to govern the flow. And so that's going to be a limiting factor.
That's what you base your calculations on.
And so this is something maybe to point out here since we've got a little bit of time. Let me check the time without running. Yeah. And that is, whenever you've got a 5-gallon bucket of solvent, like I have typically down in the bulk solvent area, don't try to pour that into a beaker or into a gallon jug or whatever, because one, you've got the hole that's not even at the edge of the container. It's going to glove and splash everywhere. So you siphon out of those. So you get a Tygon tubing. So if the jug container is about 1 foot tall, I would say get a couple or maybe 3 feet of Tygon tubing. Do you know what I'm talking about? Tygon tubing is flexible. You can pinch it. You feed that whole tube down into that jug, and it's filling with solvent. Okay? And then you have just a little bit sticking out, and you've got your container here, and you pinch it and quickly pull it down. And when you pinch it, you're pulling liquid out with it. And then you let go, and it siphons. And yeah, you do not suck on it. No, you do not. But you pinch it, And if you can't pinch it hard enough, which I have a hard time because the Tygon tubing, it seems easy, but some of the solvents are very low viscosity and low surface tension, so then they bubble back. Who was I with? I was just getting solvent. Was I with any? Wasn't anybody in here? Okay. Anyway, I was trying to demonstrate how easy this was, and it took me like 10 times. I was like, yeah, and it would flow back into the container. All right. And it'd flow back. So finally I got it, but I was afraid I was going to pull the whole tube out, and it was going to splash solvent in my face and everything like that. So that's why I get plenty of tubing down into that container so you don't pull it out. And so you pull out a little bit of it, but there's still a lot coiled in there. And then you let go, and it'll siphon into your jug, and then you don't ever suck on it. Now they make these little siphon bulbs, which I don't have one, but it'd be nice.
You can use a turkey baster.
Yeah, turkey baster too. You can stick it in there and suck a good pull on it. Yeah, but do not ever put your mouth on anything in the lab.
When you're done filling up, do you just bring the reservoir, like the container higher?
Yeah, and you'll see it slow down, and then it'll stop, and then it'll flow back into the container. It's so sweet.
So, so if you're done, you just kind of pick it up and take it out.
Yeah, it's really great. No mess, and it's great. Nobody showed me that. I just tried it one time, and it worked. I was just so proud of myself. You ever do something like that, and you're like, hey, that was pretty good. So, it may be obvious to everybody else in the world, but I was so happy that I figured that out on my own. So don't ever put like